Chapter 3 is titled Additional Applications of Gaussian Elimination. And the first section, 3.1, Gaussian Elimination Redux. The method of Gaussian elimination was in lemma GA equals U. This is now written as products of elementary matrices with extra technical information. And the theorem 3.1 is that let A be a P by Q matrix, a non-zero matrix. Then there exists a set of lower triangular P by P matrices, E1, EK, with ones on the diagonal, and a set of P by P permutation matrices, P1, PK, such that EK, PK, and so on, E1, P1 times A equals to U is in upper echelon form. Moreover, in this formula, Pj acts only, if at all, on rows J or larger rows, larger index rows, and Ej minus Ip has non-zero entries in at most the jth column. So the extra information here is the specific form of the G matrix that if multiplies A, we get the upper echelon form. So based on this theorem then, we will be enabled to separate the permutations from the E row addition matrices. And we get the theorem 3.2 that says let A be a P by Q non-zero matrix, then there exists a lower triangular P by P matrix E with ones on the diagonal and a P by P permutation matrix P such that E times P times A equals U is in upper echelon form. So it's easier to see this through an example, or if not a completely specified example, at least the sizes of the matrix are given. So if A is a 4 by 5 matrix, this is the general form, and the goal is to make it upper echelon. The most straightforward upper echelon form would be that we have the pivots in these diagonal entries and some non-zero, possibly non-zero entries above, and then the point is that below the diagonal, these red stars supposed to be cancelled out. So what this requires is, first of all, cancelling 3 entries in the first column. What we need is adding different multiples of row 1 to rows 2, 3, and 4. So this can be done with the matrix E1, which is this diagonal matrix, 4 by 4 diagonal matrix, or a lower triangular matrix, I'm sorry, with ones in the diagonal, and then ABC here. So as a result, what we get is that the first row stays the same, the second row gets A times first row, and the third row B times the first row added, and to the fourth row we add C times the first row. Now this can be written as, if you separate the identity part, I4, then this part in the first column can be actually written as the column vector 0 ABC times the row vector 1 0 0. So please check that if you multiply this out, you get a 4 by 4 matrix where every entry is 0 except these ABC entries in the first column. And then we combine it with the identity matrix to get this E1 matrix. We also have to cancel the entries under the second pivot in the second column. So that would require adding different multiples of row 2 to rows 3 and 4. And for that we need this matrix. We used these addition matrices before, but now we combine several additions into one matrix. And again, this can be obtained by adding to the identity matrix this product of 2 vectors that creates a 4 by 4 matrix. We also have to cancel 1 entry in the third column by adding multiple of row 3 to row 4. And this can be done with this E3 matrix. Now, in each of these steps, we might not be as lucky as having pivots in the diagonal entries, so we might have to switch rows in order to make sure that the numbers in the pivot positions are not zeros. That means this would be the general form that A is multiplied first with the permutation matrix, and then row addition, then possibly another permutation and the row addition, and so on. So these PIs are permutations of rows I with rows I plus 1 and so on, so the rows below. And if permutation is not needed, then they are just the identity matrices. And the point is that we are going downward, so the permutation would be permuting 1, like the ith row, with the rows downward. So that means that for I larger than j, if you multiply this EJ transpose matrix, which is a row matrix, with 1 in the jth entry and 0 everywhere, for example, this one is E3 transpose, and if you multiply this with the permutation matrix PI, then this has this form where the jth entry is 1 in the row vector AG transpose, and the PI, the upper corner, left corner, is the identity matrix of size I minus 1, and then the lower part has this permutation part, the one that actually is doing the permutation, and then on these off-diagonal parts we have zeros. Now what you can see here is that because I is larger than j, that means I minus 1 is larger than or equal to j, and when you multiply this vector with this part, ej gets picked up, and in this part, in this column, when you multiply this row with this column or block, what we get is that the permutation multiplies this 0 part, and this 0 part multiplies this part of the matrix or vector, so that part is 0. That means everything is 0 except the jth entry from this identity matrix with this 1 becomes 1. So this is a very important property. Make sure that you understand that EJ transpose times PI equals to EJ transpose. Let me actually show an example for this. So for example, E2 transpose would be multiplied with P3. This is E2 where only the second entry is 1. And P3 means that the third row is interchanged with, well, the only option is to interchange it for, permute with row 4 in this case, because PI is supposed to permute a row with other rows with higher index. But after 3, the only possibility is 4. And this is the P3 permutation matrix. This is actually permutation of the third row with the fourth row. And if you multiply this from the left with this vector, what we get is 0. Then from this first row and the second column, we get 1. And then we get 0 and 0 again, which means this is the same as the E2 vector transpose. Also, if I is larger than j, then when we multiply with the permutation matrix a vector on the left-hand side, this has the similar property that it's a Vj vector, where Vj is the same form as Uj, which means that we don't change the first j entries. Pi only permutes the lower non-zero entries. So then that will mean that the order can be changed. So if you write down that what is the product of pi with aj, where actually I is larger than j. Then what we have is that ej can be written as the identity matrix plus some vector multiplying the ej transpose vector, like the way we did this here. Then we multiply with pi term by term. So from the identity matrix we get pi, and then from this other part we get pi uj and times ej transpose. So pi uj is just some kind of vj vector, and that means that also we can replace ej transpose with ej transpose pi on the right, and then we can factor out pi on the right to get I4 plus vj ej transpose. And this has the same form as ej, so this is just e prime j times pi. They have the same form with possibly different non-zero entries under the diagonals, but the diagonals are still ones. Only the non-zero entries under the diagonal might be different. That means maybe not a, b, c, but with some other numbers, maybe not dA, but some other constants, and so on. So then the result is that all the permutations can be brought to right after A, and this E3, P3, E2, P2, E1, P1A becomes E times PA equals U. And these E's, this E matrix is the product of E3 with E2 prime and E1 prime. It's still a lower triangular P by P matrix with ones in the diagonal, since it's a combination of adding multiples of rows to rows below. So that means that this ends up to be the same thing. And then the P matrix, it's P3, P2, P1, product of permutations. It's also a permutation matrix since it's just repeated permutations of the rows. And repeating permutations will result in a new permutation. The exact same argument works in general for larger matrices. And while in a theoretical setting it is convenient to write the Gaussian elimination in this form as a product of matrices, in practice we don't do that. We just do the row operations on the augmented matrix. So this has great theoretical values but no practical value. Here's an example. If A is a n by n matrix and it's invertible, then there exists a permutation matrix P such that PA equals L du, where L is lower triangular with ones on the diagonal, U is upper triangular with ones on the diagonal, and D is a diagonal matrix. This is also called a LDU decomposition. So to show this, we could have stated this as a lemma or a proposition. To show this, we start with EPA equals U. From there, we have seen before that these matrices are invertible. So the idea is that to write this as PA equals E inverse U. So let's look at this more closely. First of all, the E matrices are these En-1, En-2, and so on, E1 matrix product. Each of these row addition matrices are invertible, lower triangular matrices, and their inverse is also lower triangular. In fact, we know more than this. We have seen before that when we have this E alpha ij matrix, and the notation here is that we add alpha times the ith row to the jth row, then the inverse of that is that we add minus alpha times the ith row to the jth row. So that means that the inverse of this E alpha ij matrix is E minus alpha ij. Exact same structure, except alpha is replaced with minus alpha in the lower triangular part. And then what we have is that L can stand, this lower triangular matrix can stand for the inverse of E, which is just the inverse of this product. And when you take the inverse of the product, the order changes. So this will become E1 inverse times E2 inverse times, and so on, En minus 1 inverse. And this is a lower triangular matrix with ones in the diagonal. Also, since A is invertible, U has n pivots. So we have a square matrix, A, and then U is a square matrix. So these pivots are all in the diagonal. If we separate the diagonal entries into a diagonal matrix, then what we get is that U, which is supposed to be upper triangular, this can be written as a diagonal matrix, where you just take the diagonal entries, times the matrix where the diagonals are ones, and then you have the same upper triangular part above the diagonal as before. So here what we get is then a diagonal matrix times an upper triangular matrix U star with ones in the diagonal. This way we get the desired result. Well, the notation changes a little bit. What we get is that this PA matrix is L times D times U star. Also, the row addition matrices EI and the permutation matrices PI are called elementary matrices in general because they result in elementary row operations. And elementary matrices might also include E matrices that are upper triangular because we can also add multiple of a row to rows above it. And this would be the Gauss-Jordan elimination part. But anyway, let's just look at through some examples how these elementary matrices work. So find the elementary matrix E and its inverse E inverse, such that when E multiplies this given matrix, this is the matrix that we get. So you have to check what happened to these matrices. From this matrix, how do you get this matrix? The first row is the same, and the second and the third row are interchanged. So we need a permutation matrix that permutes the second row with the third row. That means that E is the P32 permutation matrix, and this is how you get the permutation matrix, that you get the identity matrix, and then in the second and the third row, you switch the 2-2 entry to the 2-3 entry and the 3-3 entry to the 3-2 entry. Also, the inverse of this permutation matrix is the same as the original matrix, which is the easiest to understand if you think about it. If you want to get the identity matrix back, or the original matrix back, you have to switch back the rows 2 and 3. So after switching the rows, in order to get back the original matrix, you have to switch again, the same way. And you can also check that E times E inverse is really the identity matrix. Next example, find the elementary matrix E and its inverse E inverse such that E times this matrix equals to this other matrix. So now the first two rows are unchanged, and the third row, we get the 0 here in the 3-1 entry instead of 15. So how can we get 0? For example, we get 0 if you subtract from 15 3 times the first row, and then you get 3 times 6, 18, minus 18, and minus 3, that's plus 3, so that's minus 1. So this is adding to row 3 minus 3 times the first row. That's a row addition matrix. So the way it looks is that you start with the identity matrix, and in the 1-3 entry we put minus 3. That will add minus 3 times row 1 to row 3. From 1-3 entry with minus 3. And the inverse of that is if you switch the sign of this below the diagonal entry from minus 3 to 3, which can be also understood as saying that to undo the effect of adding minus 3 times row 1, you have to subtract minus 3 times row 1, which is adding 3 times row 1 to row 3. Next example, find the elementary matrix E and its inverse E, such that E times this matrix equals to this another matrix. So now the first row changes. This would be the backward steps in the Gauss-Jordan elimination when we go back and eliminate above this 3 the non-zero entry. Let's check that this is really what's happening. To eliminate 6 with minus 3, we have to add 2 times row 2, 2 times minus 3, minus 6 to 6. Now if you do the same thing with this entry, well, the first one, 0 times 2, it doesn't change 5. And then adding 2 times 1 to minus 1, that's minus 1 plus 2, which is plus 1. So this is really adding to row 1, 2 times row 2. And this one is if you add to the 1, 2 entry in the identity matrix, you replace it with 2. And you can also check that this is really, this multiplication is doing that the 2 times the second row is added to the first row. Its inverse is again by the same matrix, except you switch the sign of this 2 to minus 2 in order to undo the effect of adding 2 times row 2. We are subtracting back 2 times row 2. Next example, find the elementary matrix E and its inverse such that E times the matrix equals to this matrix. Let's see what happened there. Well, actually 2 rows changed. The second row, how do you get 1 from 5? You have to divide by 5, for example. And if you divide 20 by 5, you also get 4. So we divided the second row by 5. And we also divided the third row by minus 4. This, we don't use this often, or I don't remember using it before. This would be scaling rows and pivots. So there are two reasons for doing that. One is to get ones, so that eventually you can get the identity matrix in the diagonal. Ones are needed. But actually there is also a reason for that for computations. In computers, we don't want to have huge entries in the diagonals, because then if you divide with them, you can get underflow or overflows. So we want to scale the rows and most importantly the pivots. All right, so this is now a combination of two things. Dividing row 3 and dividing row 5, or multiplying with the reciprocal of 5 and the reciprocal of minus 4. So this one is, you just take the identity matrix, and for row 2, you replace 1 with 1 over 5, and row 3, you replace 1 with minus 1 over 4. So this divides the rows with minus 4 and 5. To undo this, what you have to do is multiply with the reciprocal, so it's multiplied with 5 and minus 4. And you can also check that E inverse times E is the identity, also E times E inverse is the identity matrix. Section 3.2, properties of BA and AC. So we looked at several of these properties already, either as example or exercises. We list these properties without going through the proofs of them again. Lemma 3.10, let A be a P by Q matrix and B a P by P matrix. Then A is left invertible if and only if BA is left invertible. A is right invertible if and only if BA is right invertible. We also have that the null space of A is the same as null space of BA. And B times the range of A is the same as the range of B times A. The rank of BA equals to the rank of A. the null space of A equals to 0 if and only if the null space of BA equals to the 0 vector, and the range of A equals to the FP vector space if and only if the range of BA equals to the FP vector space. You also have lemma 3.11. So this was multiplication with B on the left. Now let's see multiplication with C on the right. So if A is a P by Q matrix and C is a Q by Q matrix, then A is left invertible if and only if AC is left invertible, A is right invertible if and only if AC is right invertible. Null space of A equals to C times, that shouldn't be calligraphic, it's just regular C times the null space of A, and the range of A equals to the range of A times C. Then we also have that the dimension of the null space of A equals to the dimension of null space of AC, and the null space of A equals to the 0 vector if and only if the null space of AC equals to the 0 vector. And the last one is that the range of A equals to FP vector space if and only if the range of AC equals to the FP vector space. Section 3.3, extracting a basis. So in this problem is that if you have a set of vectors v1, vk in a vector space Fm, the problem of interest is to find a basis for the subspace V, which is spanned by these vectors, k vectors. And the way we do, the way we create a basis is that we extract the basis from this v1, vk set that spans the whole space. And the idea would be to throw out vectors that make this set independent, linearly dependent, until they become linearly independent. So using matrices and Gaussian elimination, the way we solve this is that we put together an A matrix by putting together these column vectors v1, vk into a big matrix. Then we use Gaussian elimination to reduce A to an upper echelon matrix U. And what we get is that the pivot columns of A form a basis for V. As a reminder, the pivot columns of A are the pivot columns of U, or the same columns as the columns in U, but we have to go back to A and choose the original columns. So here is an example. Find a linearly independent set of vectors that spans the same subset of R2 as that spanned by the vectors, these vectors. And actually this should be R3, I'm sorry, this typo. Since these are 3 vectors. So we have 4 of these 3 vectors. You can check, but we have seen this before, that these are linearly dependent because we have too many vectors. So the idea is that if we get a linearly independent set that still spans the same subspace, then this becomes a basis. So we put together these vectors into a matrix A, then we perform Gaussian elimination. I would like to remind you that we can avoid fractions by using least common multiples. For example, to cancel -2 using -3, what we can do is actually take the least common multiple, which is 6, and then we replace R2 with 3 times R2 plus -2 times R1. So this way we get 3 times -2 minus 6 plus -2 times -3 plus 6. -6 plus 6 is 0. Of course, we have to do this with the whole row, with the whole second row. So 3 times the second row minus 2 times the first row. We get 0 in the first entry. Then 3 times 2 is 6. Minus 5 times -2, 10. So this is 16. 3 times -2, -6. -2 is -8. And 3 times -4 is -12. And -2 times -2 is +4. -12 plus 4 is -8. then you can notice that this second row can be scaled. Still, we want to avoid fractions, so we don't divide by 16 because that would result in 1/2 here. We only divide by 8 to get the matrix with the second row 0, 2, -1, -1. And then from there, from this matrix, what we can do is add to the third row 2 times the second row in order to null this -4 out. And then what we get here is -4 plus 2 times 2, 4, 2 plus -2, 0, 1, -2 is -1. Now what you can see here is that this is already upper echelon, and the pivots are in the first, second, and the third column. So that means the basis, which is linearly independent spanning set, is the first, second, and the fourth column, or fourth row of the fourth vector of the original matrix. And the dimension of the subspace is 3 because we have 3 basis vectors. And that's the same as the rank of the matrix. Section 3.4, computing the coefficients in a basis. Here the problem is that we have V1, Vk basis for a k-dimensional subspace U of the Fn vector space. Then every vector B in this subspace U can be expressed as a unique linear combination of the vectors V1, Vk. That means we can have some scalar coefficient C1, Ck such that B equals to the sum of Cj, Vj. Linear combination of Vj's with these coefficients C1, Ck. The problem of computing these coefficients is equivalent to the problem of solving the equations AC equals B, where A is the matrix put together with the column vectors V1, Vk. It's an n by k matrix, and the C vector is the unknown coefficients C1, Ck put together into a column vector. If you multiply this out, this A times C, you get the linear combinations. And on the other side, it's supposed to be equal to B. So the way we solve this is that we solve for the coefficients by using Gaussian elimination. For example, given that this matrix is row equivalent to this matrix, and this, let's say this is supposed to be 0 here. Yeah. So what we want to write is this -7, -4, -8 vector as a linear combination of the vectors -1, -1, -1, 1, 0, 1, and -3, -1, -2. So this is actually working already backward, that we have these 3 vectors we already put together into a matrix with the augmented matrix with right hand side this vector, and then let's assume that we already did the row echelon reduction and we got this result. So reading the solution from here using notation C1, C2, C3 for these unknowns, we have that from the last row, C3 is -1. From row 2, we have -5 equals to C2. And from row 1, we have C1 equals to 5. That means that this -7, -4, -8 vector can be written as the unique linear combination of these vectors with coefficient 5, -5, and -1. Make sure you keep the same order. So C1 is multiplying the first vector, C2 the second vector, and C3 the third vector. Section 3.5, the Gauss-Seidel method. This was actually explained already for calculating the matrix inverse, but this is now put in more detailed explanation. Given a P by P matrix A, invertible or not, the Gauss-Seidel method is a systematic way of organizing all P of the calculations, AXJ equals EJ, J going from 1 to P, into one more efficient calculation by proceeding the following way. First of all, we construct the P by 2P augmented matrix, where we put together A and the P by P identity matrix. Then we carry out elementary row operations on A that bring A into upper echelon form. And we already know how to do this. This is using this E times P matrix multiplication from the left. But now we also multiply this second part, the identity part. So we get here is a UEP part. U is on the left, upper echelon, and on the right we have E times P. U is a P by P upper triangular matrix with K pivots. If K is less than P, then we cannot get the identity matrix from U, and that means that A is not invertible. So the procedure stops here. But if K equals to P, then that means that these diagonal entries UII are not zeros, as I goes from 1 to P. And then that means that using this lemma, that was about the inverse of triangular matrices, we have that the inverse of U also exists, U inverse, and it's also upper triangular, the same as U. That was a lemma some time ago. So if we multiply on the left with U inverse, then multiplying it through the matrix, we get the identity matrix, and what we get on the right hand side is U inverse EP is the inverse of A. Now, of course, we don't really want to calculate again an inverse. I mean, that's the whole point. We want to calculate the inverse of A. So instead of multiplying with the inverse of U, what we do is we perform elementary row operations until we get the identity matrix on the left here. Now, to carry out this the sequence of elementary row operations, what we really have to do is, U is already upper echelon, so it might have above the diagonal entries that are not zero. So we want to cancel out those entries above the pivots. And what we do is we use row additions. But now we are adding rows below to rows above. So now these matrices are represented with the upper triangular matrices F, because you are adding to the upper part. Once we get this, then we get that entries under and above the pivots are zeros, which means that we obtain a diagonal matrix with this. So if we cancel out the entries above the diagonal with this F multiplication, so what we get is a D diagonal matrix from U, and then on the right hand side we get something like F times E times P. So finally, to get the identity from the diagonal matrix, what we do is we multiply on the left by the inverse of the diagonal matrix. So the inverse is just this tilde D ij matrix, where the diagonal entries are the reciprocal of the diagonals entries of the original matrix D. So with this, what we get is that we get the identity matrix on the left And on the right, we get this D inverse FEP matrix, which will be the inverse of A. Note that also that, for example, the book interchanges this step 4 and 5. This can be interchangeable because D inverse is a diagonal matrix, so when you multiply with it, only the diagonal entries change. While when you are adding the rows to other rows, the diagonal entries are 1 and the diagonal entries do not change. Also note that there are theorems about when a matrix is invertible, like equivalences depending on its rank and its determinant, and possibly other conditions about the invertibility of matrix. In practice, we don't really check invertibility. Actually, the way we check it is we use this Gauss-Seidel method to try to find the inverse. So we try to invert it, and then we see whether or not it breaks down in step 3a. If it breaks down, then the inverse doesn't exist. If it goes through, then inverse exists, and we get the inverse. So here it is. See if A inverse exists, if A is this 2 by 2 matrix, 1, 2, minus 4, minus 8. So we follow the steps of Gauss-Seidel method. We augment the matrix with the identity matrix on the right. Then we carry out elementary row operations on A that are designed to bring A part into the identity matrix, or first of all, upper echelon form. So if you add to row 2, 4 times row 1, then what we get here is 0. Then 4 times 2 is 8, minus 8, 0. Then 4 times 1 plus 0 is 4. And then 1 plus 0 times 4 is 1. This is in upper echelon form. And the left part is also in upper echelon form. But since the number of pivots is 1, which is less than 2, the number of rows, that means we cannot continue with making U to be the identity matrix. And that means that at this point, the whole process breaks down, and that means the matrix A has no inverse. Here's another example to work with matrices. This involves matrix inverse, but it involves a little bit more. So for X, this matrix equation, so one matrix times X plus another matrix times X. So first we rearrange it using the properties of matrix multiplication and addition. So we bring this to the left-hand side and we factor out X on the right. Note that matrix multiplication is not commutative, so you cannot change the order. The X must stay on the right. Then we also take this matrix to the other side with opposite sign. Or you can say that we subtract this matrix from both sides. So after simplifying inside the parenthesis, we get this equation, matrix-matrix equation. So we solve this by using this as an AX equals B system, but instead of a B vector, now we have a B matrix. Still, the method is the same, kind of, as before, that we put together an augmented matrix. It's just bigger now because the right-hand side is a matrix. And then we try to reduce it to the identity matrix on the left. So for that, we use the common multiple 6 to multiply the second row and add row 1 to this. So minus 6 plus 6 is 0. Minus 6 times 4 is, plus 6 times 4 is 24. Minus 4 is 20. 6 times minus 3 is minus 18. Plus 1 is minus 17. And 6 times 3 is 18, minus 1 is 17. After this, we want to eliminate this minus 4 above the pivot. So under the first pivot now we have 0. Now here we have another pivot, 20, and we want to cancel the non-zero entry above it. So for that we use the common multiple, the least common multiple for, let's see, yeah, maybe it's not the least common multiple. Or it is, yes. Anyway, we multiplied the first row with 5 to get here minus 20, so that 20 can cancel it. But then we get from 6, 30. From 1 we get 5, and then minus 17 is minus 12. From minus 1 we get minus 5, plus 17 is plus 12. And then in the final step, we divide the first row with 30, and we divide the second row with 20. And we get here the identity matrix, and on the right-hand side we get these fractional entries. So with this, what we get is that x is this matrix here. Without the identity part. And again, you can double check this. Section 3.6, block Gaussian elimination. This is also something practical thing, that in practice there are matrices that are usually huge, but also they might have specific structure. Sometimes they are in blocks. For example, to find the inverse of this matrix, you can notice that you have a block of non-zero entries in this upper left corner and in the lower right corner. And in these other corners, we have 2 by 2 zero matrices. So this has the form A11, 0, 0, A22. And then if we calculate A11 inverse and A22 inverse, then this is a little bit less work, because just 2 by 2 instead of 1 4 by 4. And then A inverse A will be just, A inverse will be A11 inverse 0 0 A22 inverse. And you can check that this is really the case, that you get the identity matrix if you multiply A inverse with A. All right, so in this case then we need A11 inverse, and we use this augmented matrix technique, the Gaussian elimination. So we do the elimination and we get the identity matrix on the left, and whatever we have on the right, that's the inverse of A11. Similarly, to get the A22 inverse, we augment A22 with the identity matrix, and again we do Gaussian elimination until we get the identity matrix here. And then whatever we have on the right-hand side, that's A11 inverse. Then A inverse will be just putting together A11 inverse, A22 inverse, and the 0, 0 matrix. So this is a mistake. This is A22. The 4, 3, minus 1 part. Full block matrices can we also solve for their inverses. So instead of zeros, we have A21 and A12. Then what we have to do is find matrix K1 such that A21 minus K1 A11 equals to 0. And then what we do is a row operation, that row 2 minus K11 K1 row 1 to make this part 0. And this R's can be actually, this is not just one row, this is rows of rows, a bunch of rows. So then what we get here, if you multiply this first part, row part, with K1 and subtract it from row 2, here we get A21 minus K1 A11, which is 0. Here we get A22 minus K1 A12. And then the first row, block row, do not change. To get A21 minus K1 A11 equals 0, one way to do it is if you rearrange it, you see that K1 is supposed to be A21 times A11 inverse. But actually we might be able to solve this K1 A11 equals A21, even if A11 is not invertible. And that's what the next lemma says. If A is a P by Q matrix, B is a P by R matrix, and C is a R by Q matrix, then there exists a matrix K, which is R by Q, such that A equals to BK, if and only if the range of A is a subset of range of B. And also there exists a matrix L of size P by R, such that A equals to LC. This is now multiplication on the left, if and only if the range of A transpose is a subset of the range of C transpose. So for the proof of this, suppose first that the range of A is a subset of range of B, and then let EJ denote the jth column of IQ. Then the range of A is a subset of range of B, means that A times EG, which is clearly a vector in the range of A, which is supposed to be inside the range of B, then that means that this vector AEJ is a vector in the range of B, so that means that there exists a UFR vector such that this EAG equals to BUJ. This is actually then should be called UJ. And then J goes from 1 to Q. So if we put these matrix vector multiplications for several different vectors into matrix, we get that E times the matrix E1 EQ equals to B times the matrix U1 UQ. That is, since this is the identity matrix here, that means that A equals to B times K with this K U1 UQ matrix. This was one direction, showing that if the range of A is in the range of B, then we have a solution to A equals to BK. The other direction is trivial. If A equals to BK, then for any y in the range of A, there exists an x in FQ, such that y is A times x, but then A is B times K, so this is BKX, which is B times KX, and this is a vector in the range of B because it's a vector and you apply B to it. That means that also that the range of A is also range of B, in the range of B. The second part, that A equals to LC, if and only if, for the second part about this multiplication on the left, just note that A equals L times C, if and only if A transpose equals C transpose L transpose. And then we can apply then part 1 for the transpose. So we get this inclusion of the ranges, and instead of that we have to use the transpose identity, which is equivalent. So the Schur complement formulas that were discussed in chapter 1 and their generalization that are valid under less restrictive assumptions. This can be obtained by a double application of block Gaussian elimination. So this is one application of this. For example, if we have A11 matrix which is P by P, A12 which is P by Q, A21 which is Q by P, and A22 which is Q by Q. And we also have these range conditions that range of 1, 2 is inside range of 1, 1, and range of 2, 1 transpose is in the range of A11 transpose. Then we can find a pair of matrices K, which is P by Q, and L, which is Q by P, such that A12 is A11K, and A21 is L times A11. And then what we have is that this block matrix A11, A12, A21, A22 can be written as this diagonal looking matrix A11, A22 minus L, A11K multiplied from the left with this matrix and also multiplied from the right with a similar matrix. And so this is the proof. This is not a new theorem. The first part of the previous lemma can be applied to the range of A12 being in the set of which is the range of A11. This implies that there exists a K P by Q matrix such that A12 equals to A11K. Then the second part of the previous lemma applied to the fact that the range of A21 transpose is a subset of the range of A11 transpose implies that there exists an L Q by P matrix such that A21 is L times A11. So using these, we obtain that with these matrices, if you multiply out this product, what we get here is that this is A11, this is 0, this is L times A11, this is L times 0, 0 plus identity times this. And then from the right, we multiply with this IQK 0 IQ matrix. What we get is the A11, A11K, then L times A11, and L times A11K, plus A22 minus L A11K. And then using the properties that we got for these products, A11K is A21. Here we have a cancellation, so this is A22. And we have that L A11 is A21. And that finishes the proof. Finally, the last section in this, well, almost the last section. This has title 0, 1, infinity. It's just one theorem saying that the equation AX equals B has either 0, 1, or infinitely many solutions. We have seen this before already when we solved problems. Here's the proof. There are three possibilities to consider. One is that the B is not in the range of A. In that case, AX equals B cannot have a solution because AX is in the range. So that means B should be also in the range of A. But B is not in the range of A. Second possibility, that B is in the range of A and the null space of A is 0 vector. So if B is in the range of A, that means there exists a solution X such that B equals to AX is in the range of A. Then suppose that we have x1, x2 solutions to the same equation. Then if you multiply A with x1 minus x2, we have the property of matrix vector multiplication, that this is ax1 minus ax2. And both of these are B's, so B minus B is equals to 0 vector. This implies that x1 minus x2 is in the null space of A, but that equals to 0, so that means x1 minus x2 equals 0, and from here we get that x1 is equal to x2, proving that the solution is unique. And then the third possibility is that B is in the range of A, and the null space of A is not just the zero vector. So that means that there exists a non-zero vector U, which is also in the null space of A. Then if AX equals B, then if you consider AX plus alpha times U for any scalar alpha, multiplying this out, we get this is AX plus alpha times AU, but because AU is 0, since U is in the null space, this is just AX, which is B. So that means, comparing the last step with the first, is that x plus alpha U is a solution to this equation for every alpha scalar. And that means we have infinitely many solutions. The last section in this chapter is a review. This lists all the properties of Gaussian elimination and also the matrix vector products and the ranges and the null spaces. So make sure you read the review part and also use this as a reference in the future.